Hi everyone. Next we're going to review a little bit about atomic orbitals and hybridization. So recall that atomic orbitals, we talked about that when we were learning about quantum mechanics in general chemistry, where we were trying to learn where electrons really live in an atom. So we could think about an electron having a specific address where we could find it at. And Schrodinger's wave equation had solutions which gave us these wave functions which could represent what we would think of as the visual pictures or the shapes in our head for the specific orbitals where the electrons would be living. And so you might, think of a sphere for one type, but an atomic orbital specifically is a 3D region of space where there is a high probability of finding at most 2 electrons. So no matter the shape of the orbital or how big it starts to get, there's still only at most going to be 2 electrons in that 3D space. You might recall that atomic orbitals are defined, their address is defined by something called the quantum numbers. And the quantum numbers are n, which is the principal quantum number, L, which is called the secondary quantum number, m sub L, which is the magnetic quantum number, and m sub S, which is the spin. And those tell us essentially, where that electron lives in all the different spaces that we could find it, in all the different orbitals and the regions and the energy levels. It defines it. The type or the shape of the orbital becomes very important when determining reactions. The energy level N is also important too, but the shape will often determine how tightly an electron is held or how loosely it's held. And the L quantum number was given 0, 1, 2, 3, 4. It was given a number, but in order to differentiate that number from the principal quantum number n, we also gave our number a letter designation. So 0 represented an s orbital, 1 represented a p orbital, 2 was a d, 3 was an f, and technically if you had 4, that would be called a g. And we don't have that on the elements that we have on our periodic table right now. So the 2 most important ones right now are the main energy level or the size of the orbital, which is n, and the type of the orbital, which is L. The m sub L, or the orientation, will tell you how many specific orbitals of that type live within a given subshell. So in any s subshell, there's always only going to be one s orbital. In a given subshell, there will always be 3 p orbitals, and they're said to be degenerate, which means that they're all of equal energy. And you'll often see them differentiated as p sub x. Notice it lies along the x-axis. This would be p sub z, lying along the z. And then this would be p sub y, lying along the y-axis. But they're all equal energy and they're really all the same. They just have a different orientation in 3D space. And then we have our d orbitals. In any d subshell, there's going to be 5 d orbitals. And same as the p orbitals, they are also degenerate. They're all equal energy. They lie within a plane rather than lying on an axis, with the exception of this d sub 0 one. That one does have a different shape. It's a little weird looking, but they do have equal energy still. So s orbitals are spherical in shape. P orbitals are what we kind of call dumbbell. Sometimes they are called bow tie in shape. They have that node that's running through the middle of the orbital, where a node is a region of 0 electron density. And our d orbitals kind of have a clover shape. And so it's helpful to be able to think about what the 3D shape of these orbitals are when you're thinking about maybe how and why a reaction would occur and how those electrons can be transferred. So next we're going to talk about hybridization, and before we just jump into reviewing that, look at how we write electron configurations and how we build up the atom from one orbital at a time, placing 2 electrons in each orbital and then moving to the next higher energy orbital. So we start with hydrogen and we have 1s, so we have 1 electron in there. And then when we move to the next element, helium, that would be 1s2. We can at most 2 electrons in that 1s orbital, and when they pair up, their spins are paired. So you might recall that we designated that as plus 1/2 and minus 1/2. So then when we move to the next element, lithium, we have a 3rd electron to place. We can't put it in the 1s orbital, so we had to move up to the 2s orbital. And we continue this trend. So looking at our elements all the way up through oxygen, where you would have 1s, 2, 2s2, and then 2p, you would have 4. Now, when you start filling the 2p orbitals, because there's 3 of them that you can fill, the electrons go in there one at a time. So notice on boron, that first electron that's in the 2p subshell, it goes into maybe the 2px. We can think about it like that. And then when we move to carbon, the next electron after 2px goes in the 2py. These two are not paired up yet. They stay as far apart as they can until they have to possibly pair up. So remember, electrons are negative, and they both are negative. Like charges repel. So they don't particularly want to be together, so they won't be together until they have to be. On nitrogen, you've got 3 degenerate 2p orbitals, each with 1 electron in it. So now all 3 of these we would say are half filled at this point. So that next electron that oxygen brings to the dance had to go back and partner up with that first electron in one of the 2p orbitals. And so that's how it continues even as you keep building up your atom. And when you get to the d orbitals, it's that same idea. You'll have 5 d orbitals in a given subshell, but the electrons all space out and don't partner up until they have to. Another important theory that we learned is called valence bond theory, sometimes VB for short. And this is a very specific bonding theory that talks about different types of bonds that can form and then how they form and why they form. So specifically, it says when we have atoms that are sharing electrons, so covalent bonding, it occurs when we have an atomic orbital or a hybrid orbital. It can be 2, which we'll see in a little bit, on one atom overlapping with an atomic or a hybrid orbital on another atom. Each of those either atomic orbitals or hybrid orbitals must have at least one unpaired electron that when it comes together with the other one that has a single unpaired electron, those electrons can be shared and their opposite spins can come together and join to form a bond. So the atoms will be held together because the nuclei will be attracted to the electrons for each of them and they form that bond. So you have to have very specific things to form a bond according to valence bond theory. You got to have an atomic orbital or a hybrid orbital, and each one of them has to be half filled, meaning it has to have 1 electron in it. So when it overlaps, it can overlap with the other one that's half filled. And we formed very specific types of bonds when this happened. So for reviewing purposes, we'll start with the simplest of models here. We can look at the covalent bond that's formed in hydrogen, H2. So imagine if you were to write out the electron configuration for hydrogen, you would have just 1 electron, so it would be 1s1. And if we have H2, let's also think about the Lewis structure. Very simple. We have 1 covalent bond that's between each of the hydrogen atoms. So when we're talking about using valence bond theory to describe the bonding in H2, that covalent bond is the bond we want to describe. We have 1 single bond, and we're going to describe it a little bit more in depth than just saying it's a single bond. So each hydrogen atom brings a 1s orbital to the dance, and notice that each of them are half filled already. So this is good. This makes it simple. We have 2 half-filled 1s orbitals that can essentially approach one another and start to overlap along what we call is the internuclear axis. You can think about it like an imaginary x-axis running right through the center of your orbitals. So this is called the internuclear axis. And so as those 2 1s orbitals start to approach one another along that internuclear axis, there's going to come a point where they start to overlap. And that region of overlap right here is where those 2 electrons are going to come together with their spins paired. So plus 1/2 minus 1/2, which we represent as up arrows and down arrows. And that represents our bonding region. So this region of overlap is our bond, and it has a specific name, this bond. This is called a sigma bond. A sigma bond represents a single bond, which is what we have in hydrogen. We have one single bond, we said. And so a sigma bond is very specific. It is where you have this overlap that occurs directly along the internuclear axis. And so another way to think about it is overlap in one location. So we only have overlap in one spot, and it's direct along that axis. It's only in this one place. And so that is the type of bond that's formed in H2. We have that single sigma bond, which you can also use the Greek letter sigma to represent that as well. And that's our covalent bond in H2. Typically, I would draw this type of a model that you see right here with the two spheres, but sometimes you'll see where they spread them out and draw them more like an elongated hot dog, where the sigma bond is that region between the two nuclei. But I think it's easier to see in the top image right here because you can see that actual region of overlap that you're looking for when predicting the bonding using valence bond theory. So valence bond theory would tell us something like this. You know, we have one hydrogen overlapping with another hydrogen atom. Each of them has a half-filled 1s orbital, and as they overlap along the internuclear axis directly, they form a single sigma bond. So they have that one region of overlap there, which is contributing to that sigma bond. Now let's compare the easy valence bond theory bonding that we saw in hydrogen with something just a little bit more involved, methane, CH4. So if we look at how we're going to have our orbitals overlap, we want to think about what specific atomic orbital each atom would be bringing to the dance, how they have their half-filled orbitals that can come together so the electron spins can be paired. And sometimes it's not as obvious. So the structure of methane is a tetrahedral arrangement where we have 4 hydrogen atoms bonded to a central carbon atom. And the electron configuration for hydrogen, as we said, is 1s1. And for carbon, we're going to have 1s2, 2s2, 2p2 for our electron configuration. And when you look at the energy diagram for carbon, it looks like all carbon really has to bring to the dance is 2 half-filled 2p orbitals. So how can it overlap and form 4 equal energy bonds? Because we have 4 sigma bonds we have to describe here, 4 single sigma bonds. How can it form those if it only has 2 half-filled orbitals? And methane is alive and well. Methane is natural gas, so it does exist. And it exists in this tetrahedral arrangement that we are fairly familiar with bond angles of 109.5 degrees between a hydrogen, carbon, and hydrogen atom. So this is where we dive into hybridization and why it's so important, because there are so many molecules that exist that don't look like they should technically if you just look at their energy diagrams and what the number of unpaired electrons they have is. So we need a carbon atom with 4 equal energy, half-filled hybrid orbitals. That's what we need to form in order to have this methane molecule. So how this will work in order to have those 4 orbitals available for overlap is first we're going to excite an electron from the 2s orbital and promote it up to that empty 2p orbital. So the first step is excitation. Notice by just exciting 1 electron from that 2s, now we're left with a total of 4 half-filled orbitals. They're not all equal energy. 3 of them are 2p, 1 of them is 2s, but we're on our way. At least we have 4 half-filled orbitals that are available for overlap. Our next step is to think about making them all equal energy. by mixing them together, or in other words, hybridizing them. So next, our 4 atomic orbitals must become 4 equal energy hybrid orbitals. So imagine taking all 4 of these, the 1, 2s and the 3, 2p orbitals, throwing them together, mixing them, hybridizing them in other words. And when you get them out, you get 4 degenerate new hybrid orbitals that are all equal energy. And we have to give our new hybrid orbitals a new name. So we name them based upon the atomic orbitals that were thrown into the mix. And in our example for methane, the atomic orbitals that we threw into the mix were we threw an S and we threw 3 P's, specifically 3 2p orbitals, but I'm just dropping the 2 term out front for now. And so we call them S, P, and then superscript 3. So these would be 4 equal energy sp3 hybrid orbitals. And so now carbon has 4 of them. They all have 1 electron in them, and they're ready to bond and overlap with the half-filled orbital that's on hydrogen in order to form our molecule methane. And what should the shape of an sp3 hybrid orbital look like? Do you think it would look more like an s orbital, which is a sphere, or do you think it would look more like a p orbital, which we said was a dumbbell? So when we think about what we're throwing into the mix, when we hybridize, we have a larger contribution from the p than we do from the s. So our sp3 hybrid orbitals are going to be 25% S character and 75% P character if we were to look at it out of 100%. So they're going to have a little bit more of a shape compared to a P orbital than they will an S. They'll actually have one node that is just a little bit bigger than the other due to the fact that an S we said is a sphere and a P orbital is a dumbbell. So one end's kind of like an elongated or a little bit of a larger sphere that has the little bit more of the S character, but it still has that overall dumbbell shape. It's 75% P orbital. And there's a node running through the middle, just like there would be on a P orbital. So it acquires that characteristic as well. A lot of the hybrid orbitals, sp, sp2, sp3, have this shape. Some of them just have a little bit less P character as we go along. Okay, so now that we've seen how carbon's 4 atomic orbitals can become hybridized to form 4 new equal energy hybrid orbitals, we can actually see how the bonding will occur in something like methane to form that tetrahedral arrangement according to Vesper. So what we will have is we'll have a 1s atomic orbital on each of the 4 individual hydrogen atoms, and those will overlap with the 4 new sp3 hybrid orbitals that are on carbon. So when we're looking at our picture, you can imagine you have a bunch of different internuclear axes, like this would represent one, this would represent one, here and here, each all coming along the corners of a tetrahedron shape. And so what we end up with then is our 109.5 degree bond angles, everything spaced out as far apart as it possibly can be. We have a single sigma bond between an sp3 hybrid orbital on carbon and a 1s orbital on our hydrogen. We have another sigma bond between another sp3 hybrid orbital and another 1s orbital. We have a third sigma bond between a 1s and an sp3. And lastly, we have a fourth sigma bond between the final sp3 hybrid orbital and a 1s on hydrogen. So in total, we formed 4 sigma bonds when forming methane, which is what we expected from looking at the Lewis structure. 4 sigma bonds means there's 4 single bonds in that molecule. Now we'll look at different ways that our molecules will change when we have sp3 geometry on the central atom, but maybe we have a little bit of a different molecular geometry than tetrahedral. So methane, all the bond angles were 109.5 degrees. All of our outer atoms were hydrogen and they were all the same. And so we didn't have any lone pairs on the central atom. Now, if we compare that shape, that tetrahedral shape, to something like ammonia, which is NH3, the nitrogen central atom still has 4 equal energy sp3 hybrid orbitals on it. It's just that now one of those sp3 hybrid orbitals contains a lone pair of electrons within it. So 3 of them are being used to overlap with hydrogen to form 3 sigma bonds, but one of those sp3 hybrid orbitals has this lone pair living within it, because a lone pair of electrons also has to reside within an orbital. And remember, that lone pair kind of pushes down and shrinks the bond angles a little bit, so now they're about 107 degrees apart. Next, we can think about how it will look when we remove another bonding pair and replace it with a lone pair. So oxygen, in the scenario of H2O, oxygen is using sp3 hybrid orbitals to bond. In this case, 2 sigma bonds are formed, and 2 of the sp3 hybrid orbitals are overlapping with hydrogen. But we have 2 lone pairs on oxygen, and those lone pairs also live in their own sp3 hybrid orbitals as well. So with our tetrahedral geometry, all 4 hybrid orbitals are being used for bonding. In trigonal planar, 3 of the sp3 hybrid orbitals are being used for bonding. 1 is being used for a lone pair. And in something like water, where we have a bent shape, 2 are being used for bonding and 2 are being used to house lone pairs. But you can see how all 3 of these shapes are based upon that tetrahedral arrangement. And then with water, now we have 2 lone pairs that are pushing down and shrinking those bond angles even more. So we end up with about 105 degrees between our hydrogen, oxygen, hydrogen bond angles there. Okay, now we're going to look at a molecule just a little bit more complicated than our methane. We're going to look at ethene, which is C2H4. So ethene, which is sometimes called ethylene, has a Lewis structure where we have a carbon double bonded to another carbon, and it's symmetrical. Each outer carbon has 2 hydrogens bonded to it. But basically what we want to do is we want to describe this double bond between the carbon and the carbon. That's what's really going to make this different from methane, where we just had single bonds. And each carbon is pretty much trigonoplanar because it's bonded to 3 things. And the molecule is planar. That means it lies in a plane. It's flat. So it has a top face where something could come down on it, and it has a bottom face where something could come up from it. That's why it's showing it laying in that paper that you see there. So in carbon, it needs to be bonded to 3 other distinct atoms. So for example, if we're looking at this carbon on the left, that carbon needs to form a bond to hydrogen, and to this other carbon here. So those are the 3 things that are around that middle green carbon. So what we're going to need are 3 equal energy hybridized orbitals that are going to come from the atomic orbitals. So let's now imagine that we start with our electron configuration, or our energy diagram for carbon. Originally we needed 4, and this time we only need 3. So what we're going to do is we're going to mix together our lowest energy 2s and then 2 of the half-filled 2p. This right here, this orbital is unaffected. After we promoted that 1 electron up to the 2p, it's still there, but we don't need to throw it into our hybridized mix because we don't need it. We only need 3 to equal energy hybrid orbitals this time. So that unaffected 2p orbital, or in other words, unhybridized, is very important, but we don't need to throw it into the mix. So we mix together this time. We mix an s and we mix 2p atomic orbitals. And so now we got to name our new hybrid orbitals that are all equal energy, and we're going to call them sp2. So we get out 3 equal energy sp2 hybrid orbitals, and we're still left with that unhybridized 2p atomic orbital. So we have our 3 hybrid orbitals, and we have our 1 atomic orbital. And what's important about forming a double bond is that unhybridized atomic orbital has an electron in it, so it's half filled. If it didn't, we couldn't even form that double bond in the first place. So let's look at what the shapes of our hybrid orbitals and our leftover atomic orbital will look like on one of our carbon atoms. So you can imagine in the middle right here, this is where one of those carbon atoms would be. We have in a trigonal planar, so 120 degrees apart from our carbon atom, we have our 3 sp2 hybrid orbitals. So we got 1, 2, 3 of them. And each of them have 1 electron. So 1, 2, 3. They're ready to overlap with something else. And then we have left over, which is represented with a red and a blue sphere, our unhybridized 2p orbital. And that unhybridized 2p orbital is also ready to go. It is half filled with 1 electron as well. So each carbon is going to bring a picture just like this to the dance when they come to overlap. This is what each carbon will have. So remember, we have to form a double bond. So if we just redraw our Lewis structure really quick for ethene or ethylene, we have to describe the bonding, and we have to describe more than just a sigma bond at this point. We're going to have quite a few sigma bonds that form, but we're also going to have another important new type of bond. So between an sp2 hybrid orbital and hydrogen on each side, we form 2 sigma bonds right there. That would represent the single bonds that we see at the top. And we're going to have those on each side. So all 4 of those are represented by single sigma bonds. And those represent sp2 hybrid orbital overlap from carbon and 1s orbital overlap from each of the 4 hydrogens. And then along the internuclear axis, so directly along our imaginary X internuclear axis, 2 of the sp2 hybrid orbitals from each carbon are going to overlap. And they're going to overlap directly. So they overlap right along that internuclear axis. And so that also represents another sigma bond. So one part of a double bond is part sigma bond. We have that direct overlap that you see right along that axis in one location. But the other part of our double bond is what happens with those unhybridized p orbitals that have 1 electron each in them. And so you can see in this picture on the right a little bit better, imagine how those could overlap in space, and they overlap in 2 locations. They overlap above the axis and below the internuclear axis. So they overlap sideways rather than directly. And that sideways overlap is called a pi bond. And the only way that you can form pi bonds is by having unhybridized p orbitals overlapping. So you're never going to form a pi bond from direct overlap, and spheres like s orbitals always are going to overlap directly. They can never overlap in 2 locations because they don't have a node. P orbitals, remember, have a node running right through the middle of them, so they can overlap sideways. P orbitals also can overlap directly when they overlap like this. That would be an example of a sigma bond being formed from p orbitals overlapping, but the only way that you can have orbitals overlapping sideways is by having unhybridized p orbitals overlapping like you see in the picture on the right. So that sideways overlap above and below, so right here and right here, represents the formation of 1 pi bond. So our double bond in the middle is made up of a sigma bond plus a pi bond. Anytime you see a double bond, that represents 1 sigma and 1 pi bond together, whereas a single bond is just a sigma bond. A double bond is a combination of those 2. And for the grand finale, building up all the way to acetylene, which is an alkyne, it has a triple bond between the 2 carbons. We want to use our knowledge to describe the bond there. And so really this is just an extension of what we just saw with ethene. So in this case, we have C2H2. If we imagine that, one of our carbons is our central carbon, it's bonded to a hydrogen and it's bonded to another carbon. So it's bonded to 2 things. rather than 3. So the hybridization of that carbon is going to be sp. Same with the other carbon. It's going to be sp hybridized. We only needed to hybridize 2 atomic orbitals and throw them into our mix. And what we are left with then is 2 unhybridized 2p orbitals. That each are half filled, whereas last time we were just left with 1 unhybridized orbital. So now let's look at what the picture for something like acetylene would be. It's very similar. We have right here in the gray, this would represent one of our sp hybrid orbitals on one of our carbons. That's going to overlap directly with a 1s orbital on hydrogen, forming a sigma bond. So that could be our sigma bond right there. And we'll have the mirror image on the other side, an sp hybrid orbital overlapping with a 1s on hydrogen to form a sigma bond. Here's our other sigma bond. But now we want to say, what is our triple bond made of? Well, the easiest thing in the middle first is the sigma bond formation. We have sp from one carbon and sp from the other carbon. That overlap occurs directly, so that overlap represents a sigma bond. When you have sp-sp overlap, that equals a sigma bond because it's directly along the internuclear axis and it's only in one location. And now we have to consider those 2 unhybridized 2p orbitals that didn't get thrown into the hybridization mix. They're going to lie 90 degrees apart from one another. They're going to be perpendicular. So this orbital right here would represent one of the unhybridized 2p orbitals. And there's going to be 2 on each carbon. So a total of 4. This would represent another. So those 2 that are in, we can call it the z-axis, lying along the z-axis, those would represent forming 1 sigma bond because each has a half-filled orbital that those electrons can overlap. Then, now running behind and forward, there's another half-filled unhybridized 2p orbital. And they each have 1 electron in them. They can overlap to form another pi bond. So a triple bond is going to be made up of a sigma bond plus 2 pi bonds, whereas a double bond was just a sigma bond and 1 pi bond. So every triple bond that you see, you can always assume that it's going to have those 2 things, 1 sigma and 2 pi's.